Hello everyone. So today this is the lecture number 1 for the module 6, that is input output module. In this lecture I am going to talk about the IO module and its function and its structures, the requirement of the IO module and the IO module techniques. IO module basically provides interface to the outside world. Our computer connects, how computer connects to the outside world, means all the peripherals which used to attach to the computer, how these peripherals can communicate to the processor or how processor can communicate to these devices. Because the IO operations are accomplished through the wide variety of external devices. There are a lot of devices starting from keyboard to printer to your disk and other devices like mouse, monitor, etc. And it is used to transfer the data between these devices, peripheral devices, to the computer and from computer to the peripheral devices. And these devices are connected to the processor via an interface circuit. It is not a direct connection between the processor or between inside the processor and the outside these peripheral devices. So this interface circuit is also called as a IO module. Now the very first question is why this IO module is required. Why don't we connect these peripheral devices directly to the computer or to the rest of the system without any interface circuit? So the first reason for this is there is a wide variety of peripheral devices are there. Means a lot of devices, it can be even hundreds of devices can be connected to the system. So it is impractical to incorporate the necessary logic because each device have its own way of interacting to the processor. Way in the sense the data, they deliver the data in different sizes at different speeds and in different formats. Let us say keyboard, if you input something from the keyboard, it will take 8-bit data at a time. One key is pressed, 8-bit data will be there. If it is a communication between a hard disk and the processor, then the data size will be large. Let us say one block of data, that is 512 bytes, typical size of the block. So due to this reason, so all these, and that is the one thing. Another thing is the format of the data is another. Let us say keyboard takes the ASCII data. Some other devices like they can take the data in other formats. So due to all this reason, it is impractical to incorporate the necessary logic within the processor for all these different types of devices. So we need an interface circuit between the connection processor, between the processor and these peripheral devices. An interface circuit that will take care of all these things like speed difference or format difference or the amount of data in terms of the word length and all. Another thing is there is a speed mismatch between the processor memory and the IO devices. Some devices can transfer the data at higher rate than the processor can do or the processor speed, and some devices are slower than the processor. Slower device example, let us say keyboard is a slower device example. Fast device example is the hard disk. Hard disk can transfer the data at higher rate compared to the processor or memory operation. So another thing is that a speed mismatch between the processor memory and IO devices. So some devices are faster than the processor and memory, that memory at the rate at the memory can do the operation. Memory means here the primary memory, and some devices are slower than that. So slower device example is keyboard, and a faster device example let us say is the hard disk. So hard disk can do the data transfer at a higher rate compared to the processor can handle it. So, the speed mismatch is from the both sides. So, these are the few reasons. Due to this, we need an interface circuit that take care of all these problems. So, look at how a generic model of I/O module looks like. So, in this model you can see, so right now I'm not mentioning anything about what is inside in that, but how it is interfacing to the system, and system means the processor and the memory. So, it is connected to the processor and memory via the system bus. This is a system bus, address lines, data lines and control lines are there, the complete system bus is there, and to the outside world it is connecting to there are links to the peripheral devices. These are the links. So, one I/O module can handle more than one devices, or it can take care of more than one devices. So, and this is your I/O module or the interface circuit. Interface circuit. So, this is a generic model of any I/O module. Now, we look at what is inside this I/O module, or what exactly inside this interface circuit is there. So, let us look at the functions, what functions are accomplished by the I/O module. So, first is the control and the timing. It coordinates the flow of traffic between internal resources and external devices. Internal resources means processor and memory, external devices means the peripheral devices for which this interface circuit or this module is there. And it sends the control signals, or send and receive the control signals like read, write, ready, busy, error, all these control signals it understand. So, some control signals are coming from the processor, let us say for reading from some device, processor will send the read signal. That read signal has to decode by this interface circuit and understand, okay, this is a read signal, and then at the appropriate device as per the address provided by the processor, that device has to be selected by this module if this module is supporting more than one devices, and then accordingly it will communicate to that device and check the status of that device. If the device status is okay, then it will read the data from that device, put into the buffer and give to the processor. So, this is the overall role of this. So, all this function, whatever the control and the timing require, that is done by this function, done by this module. Next is the processor and the device communication. As I said, to do this controlling and timing, it has to communicate or do any data operation or data transfer. It has to communicate with the processor as well as communicate to the device. So, the communication between device and the processor is also done by this module. The processor communication particularly involves the command decoding. Whatever command is coming, that command has to be decoded, that will come through the system bus, control lines of the system bus, and if it is a read operation, then after reading the data from the device, it has to put in some buffer that data, so that data can be fetched by the processor, and it has to tell the status of the device also can be read by the processor through this interface circuit, and the address recognition, that is the most important part. Processor places the address on the address bus, and that address has to be recognized by this module. After recognizing, it will contact to that device and get done the operation. Then, to overcome the speed mismatch, the data buffering is also required. As I said, the devices, there is a speed mismatch between the devices and the processor, or you can say the external world and the internal to the processor, speed mismatch is there. So, to overcome this, we need a buffer. So, the buffer also is provided by this interface circuit or the module, and if there any error is detected, maybe that device physical device is currently out of order, let us say in a printer maybe the paper jam is there. So, that error has to be detected, it has to report to the processor so that processor can indicate the error message. Similarly, for the hard disk, the disk bad sector has to report it. If it is there, then it has to be reported as well. So, it also detect the error as well in the occurred during the operation, for that particular device. So now look at what is the general I/O module structure. What is inside this interface circuit, or what is inside this module actually. So in this module you can see, first of all, it has the interface to the system bus. Through that it connects to the system bus and then connect to the processor and the memory, and one interface is for the external device, the device which is supported by this particular module, maybe one or more than one. So, and it has the data register, in which the data, suppose in case of the read operation, processor initiate a read operation. So after reading the data from the device, it will keep the data into data register. So this is a buffer. So from there it can go to the via data line of the system bus, it can go to the processor. Processor can find out the status of the device or send any control signal. For that, to get the status of the device, it has the status or control register, and processor supply the address through the address lines, and after recognizing this address, this is I/O logic. I/O logic will identify the address, because maybe this module is supporting more than one devices. So the address for current operation, the address belongs to one of the I/O devices or one of the peripheral devices to which it is connected. So it will identify the address, and then out of these external devices, so here the external device interface logic is there, and each interface logic for working for a individual device. So here to device it has the data lines, status lines and control lines. Through that it accept the data from the device, as well as supply the data or give the data. If it is output device, then this data processor is giving some data that has to be write to that device. So the both way communication is there, and the device status it can read, so through the status lines, and it can send the control signal, say for example spinning the disk. So for spinning the disk it will send the control signal, so the disk will spin. So that's the part of the control logic. And here towards the interface to the system bus, the control lines are there, address lines are there, data lines are there, through that it is connected. So for any operation, first CPU checks the I/O module device status through this status registers, and then I/O module returns the status, whatever the status of that device is there, it will read the status from there, and if the status indicates that okay, it's ready, then CPU requests the data transfer. Then I/O module gets the data from the device. Definitely in the meantime, address lines, processor supply the address to the address lines, and that address will be recognized by the module, and appropriate device will be selected, and that device will be requested to give the data, and that data will be read from the device and put into the data register. Then finally, after getting the data from the device, then I/O module transfer the data to the processor. So this is the whole operation, how this I/O module works. Now to do this, processor communicates to the outside world or communicate to the peripheral devices. For there are three methods are there. One is a programmed I/O, through the programmed I/O connect, and second is the interrupt driven I/O, and third is the direct memory access. In the today's lecture, or this particular lecture, I am going to talk about the programmed I/O and the interrupt driven I/O. Direct memory access will be in the next lecture. So let's start with the programmed I/O, how the programmed I/O works. So in the programmed I/O, CPU has the direct control over the input output devices. Definitely it is through the interface circuit only, but direct control in the sense, right from initiating the operation, I/O operation, that says sensing the status, then read write, issuing the read write commands, and then finally transferring the data. Until this complete operation is not over, processor is actively engaged in the operation. So first processor issue the command to I/O module, and then read the status of the I/O module, and if the status says that okay, it is not ready, and it will loop continuously checking or periodically checking the status of that device. Once the device status indicates that it's ready, if some error condition is there, then it will be displayed and the operation will be terminated immediately. But if the status indicates that okay, it's ready, then it will read word from the IO module, means interface circuit will or module will be request to the device to get the word, and that word will be put into the data register, and from there the processor will read the word from the module, and after taking or fetching the data from the module, that data will be returned to the memory. So this completes the one operation and then it is ready for the next operation. So in the whole process we have seen that CPU waits for IO module to complete the operation. Now what are the commands which use by the processor or initiate by the processor? One is a control command that telling module to what to do. Let us say read is a one command, read or write. Or checking the status of that device, that is for the test command to check the status of the device, then issuing read write operation, read write command. So in control, so all these set of commands are initiated by the processor, and so in this whole process we can see that processor waits, the processor time is wasted. Why the processor time is wasted? Because these devices are as I said, some devices are slower compared to at the rate at which the processor can work. Say for example keyboard, if the program the one input has to be taken by the one character input has to be taken by the user. So user will press the key, by the time user will press the key, maybe the thousands of cycles of the processor will be wasted. Command initiated, user will supply, it will take few seconds. In the seconds means processor speed is usually some gigahertz. So you can imagine that how much time of the processor time is wasted. One cycle of the processor is very costly. Means it do something in that, you can do in a one cycle, and maybe that cycle is a nanosecond of duration. So in 1 or 2 seconds how much work processor can do. So here the processor is actively engaged in the complete IO operation in the programmed IO. So this wastage of time is there. So later we will see that how this wastage of time can be saved, and can this time be utilized during the time where the device is getting ready to provide the data. Can processor do some other work? That we will see that is there any other mechanism that provides this facility. So now in the programmed IO, one of the important thing is how the IO devices are addressing. Memory, we know that how the processor wants to get some data, or some data has to be read from the memory. Then what is the mechanism? Processor generates the address that belongs to this memory module. Let us say memory, I have some 1K memory, so starting location from 0 to let us say 1K locations, total 1K locations are there. So 1K locations means I need 10 bits to locate any data in that. So 10-bit address will be generated, and that will be identified by the memory. So memory, any data in the memory can be identified through this a unique address which is associated with each data element stored in the memory. Similarly, for the IO devices also we need some unique identifier. It can be it is also like an address only. So there are the two mechanisms. One of the mechanism is the memory mapped IO, means devices and the memory share a common address space. Let us say that total 1K locations are there. Out of 1K locations, 1K locations means 2 raised to power 10. So total 1024 addresses are there. Out of 1024 addresses, let us say 512 addresses are used for addressing or storing the data and instruction in the memory, and remaining 512 addresses identify the IO devices. These are reserved for the IO devices. So same address space is used. So in this particular kind of addressing mechanism, IO looks like just a memory. IO operation is similar to the memory read write kind of thing. So, for IO, let us say input and output, so corresponding memory operations are read and write. So, there is no special command for IO, same commands or same instructions which are used for the memory in the program can be used for the devices, because as per the processor's view, there is no difference between the memory and the IO. Only the address, through the address it is differentiated, and the rest of the things will be taken care by the corresponding interface circuit. So, what is exactly in the what address? Address means for each device you have the data register, you have the status register, that will be the address of that. So, maybe one device is consuming 2 addresses, 3 addresses, 4 addresses, depends upon the buffer size and other control circuitry, and that will be taken care by this module, IO module, that is associated with that particular peripheral device. So, here what is the advantage of this memory mapped IO? The advantage is all sort of memory operations. On the memory, the operations can be the same operations can be do with the IO as well. So, the large variety of operations can be done, because for memory the instruction set provide lot of instructions. You can reference the memory in different way. So, the same instructions can be used for the IO as well. So, as for to the programmer, the wide variety of options are there to write the program. So, this is I am talking about the assembly level. Assembly level only we can visualize all these things, assembly language level. Second is isolated IO. Isolated IO means address space is separated. There is a separate address space for memory and separate address space for the IO. So, in this case we need a separate IO commands. So, here the memory read write are not same as an taking input and output from the IO. So, the separate commands are same commands cannot be used, separate commands will be used, and we need some lines in the bus that indicates okay, this is the IO selection line and this is the memory selection line. So, we need some lines through that the distinguish between the, because address number 1, 2, 3, 4 can be in their main memory as well, and address number 1, 2, 3, 4 because a separate address space is there. So, that 1, 2, 3, 4 can be there in IO as well. So, before communicating to any IO device or memory, first the select line has to be select, that indicates whether this operation, the current instruction is for the IO or it is for the memory. So, let us look at this, what is the difference between memory mapped and isolated IO, how these two works. So, here you can see there are the two, this is for the input device which is keyboard. Input data register is there stored at the memory address 516 and at the address 516, and address 517 is for one buffer is there, that is tells the status register for the status and control register for the keyboard. So, now for memory mapped IO, let us say the instruction, this is the address where the instructions are stored 200 and 202. At 200 instruction is there load AC. Load AC, AC stands for the accumulator register, load AC with the operand 1. So, AC register value or AC register will be loaded with the 1. So, AC register loaded with the 1 means here it will come, AC will contain 1, AC register size is let us say 16 bits. So, 1 value will be stored, AC size. So, 1 value will be stored, and you know that here 1 means it set to 1 means start the read operation, and then this AC value, AC is now current value is 1, this AC value is stored in the location 517. So, 517 will contain the 1 and that 1 indicates okay, it is a read operation. So, initiate the keyboard read, then load AC, AC value will be loaded with 517. So, through that it will get the status byte. So, that this bit here tells the status, if this bit is 1 then it is ready, otherwise if this bit is 0 then it is busy. So, then it is checking branch if sign equals to 0. This 8-bit data if I interpret as an signed word or signed data, then this will tell me the sign of that. Leftmost bit is always tell me the sign of. If the sign is 1, then it is ready. If the sign is 0, then it has to branch to 202 again, and is continuously check. Once continuously check the status of this keyboard, and once the status becomes the 0, status bit indicates 0 means it is status bits indicates 1, then means it is ready. So once it is ready, then ready means that the keyboard data register contain the data which is read by the which is keyed in by the user to the this input data register, and from this, from the location 516, the AC register loaded. AC register loaded with the value of 516. 516 contains the keyed in by the user. So this is the way how the 1 byte of the data is read from the keyboard. So all the instructions you can see, all these instructions, load AC, store AC, and this branch if sign or load AC, all these instructions are applied to the memory as well. Same thing can be done as for the memory as well. Memory also you can load accumulator from some memory location and then store the data. So all these instructions are can be used for the memory operations as well. So that is in the case of memory mapped IO. There is no difference between the memory operations or any input output operation. But in case of the isolated IO, the separate instructions, load IO, test IO, branch not ready, in, out, all these instructions are different. So the separate set of instruction, and usually that instruction have the limitation in terms of less number of instructions are there. You have to, because you have to devise here the different instructions if you are using isolated IO. For memory mapped IO, the same instructions can be used, so you don't have to devise the separate instructions. So in that sense, memory mapped IO is better. But because it share the address space, memory address space, so the some memory locations, it reduce the memory address space, because some portion of the memory address space is used by the IO devices. So the memory address space will be restricted in that case. So that's the limitation of that. So this is the difference how the memory mapped IO and isolated IO works. So that's the one technique. One technique, IO technique, through that processor can communicate to the peripheral devices. Second technique is interrupts, through the interrupts. So first we look at what is interrupt exactly. Interrupt means, it says that interrupts what the processor is doing. Where our processor is doing work, at that moment stop. Some signal is there that indicates to processor that stop the current operation and do something else. That's the interrupt. It can be internal to the, it can be generated signal, that signal can be generated by the processor, inside the processor, or from the outside world as well. Inside the processor means through the program, maybe some overflow has occurred, maybe the data cannot be accommodated in the required number of, in the given address size. So the size of the data is more, so that's overflow, division by 0, segmentation fault, all these are examples of the internal interrupt. Interrupt may be generated by the timer device. For example, in the preemptive multitasking operation, in the preemptive multitasking that is used, timer is used. When the time is over, then the process stop that one operation and do the some work on the another process. As I said, the IO devices also can generate the interrupt signal, indicate to the processor that okay, whatever currently you are doing, that you stop it and do the another task. That task may be related to the IO. Interrupt can be generated by a failure of hardware device, let's say memory parity error. During the read operation of the memory, maybe the parity is not matched. Parity is not matched means the data is corrupted due to the physical impairment in the device or whatever the other reason. So means the data is not valid. So now, then if it is not valid, then that has to be indicated to the processor, such that that device, that data, it should not take it, otherwise it will produce the wrong result. So these are the few examples of the interrupt. Now how this it is related to the IO, means how IO can be done through the interrupt using the interrupts. So, using the interrupt mechanism, how the I/O operation can be done, that we will see now. So, here CPU issues a read command to the I/O, let us say. After issuing this read command, because the I/O devices, most of the I/O devices are slower than the processor. So, after issuing command, the device will take some time to get ready with the data. During that time, as in a programmed I/O, processor is just waiting for the device. So, waiting in the sense processor periodically checking the status register of that device. If the status says is ready, then it will fetch the data from there and store the data into memory and come back to the normal operation or next instruction. But here that happens in the programmed I/O. But in interrupt driven I/O, what is the difference? Processor issues the read command, and after issuing the read command, it is doing something else. So, doing something else means, in the multitasking environment, the multiple programs are stored, loaded in the memory. So, for one program maybe some I/O operation is required, so that it will be stuck to that. So, during that time this I/O, the device is getting ready, the processor can switch to the another program and it can do another execution of other programs. So, processor time will not be wasted, utilization of the processor will becomes better. So, once the device is ready with the data, means the I/O module gets the data from the peripheral. So, during getting that data, the processor is doing some other work, and once the module is ready with the data, module interrupts the CPU, and that interrupt will indicate that okay, the requested data is now available, you can take it. So, here the difference is what? Difference is the device or the module is sending a signal to the processor that indicates I am ready with the data. In programmed I/O, device is not sending anything, everything has to be done by the processor. Processor have to continuously monitor that status register, device from its own side nothing is sending. So, that is the difference. So, now once the processor is interrupted, processor got the signal, that interrupt signal that indicates okay, I have to stop. Then processor have to save the context, whatever the current program it is running. So, the PC value, current PC value and other processor registers, they may have some temporary results computed for that program that has to be saved at some location such that it can be restored after finishing this I/O operation. So, once doing this, saving the context, then processor jump to this I/O service routine program or the interrupt handler, I say interrupt handler program, it is called as interrupt handler, interrupt handler program. So, this interrupt handler program is nothing but it is a sequence of instruction to execute, to finish that reading the data from that device, from the module, and put into the appropriate location where it was supposed to be there. So, this is the way how it works, interrupt driven I/O. Now, important thing is when processor can be interrupted, because we know that the instruction execution have some discrete steps, fetching the instruction, fetching the decoding the instruction, fetching the data, then doing the operation, storing the result and so on. So, these are the we have seen in the instruction processing cycle. So, when processor will check this interrupt signal, processor will check the interrupt signal only after the completion of the current instruction execution. It cannot be stopped in between, let us say fetching the data state. So, processor always after completing the one instruction cycle, it will check is there any interrupt is there. If the interrupt is there, then it will do this context saving and jumping to the interrupt handler program, means PC will be loaded with, because each device have its own interrupt handler program. So, it will jump to that location, PC value will be loaded with that location, and then it will execute one by one instruction to complete that task, and then again it has to come back to the original program, means original means the processor was doing before this interrupt occurred, the location from where the context was saved, it will take the data from there, all this PC value, register value, and start execution from that point onwards. So in interrupt, we will see that how the program flow control is there. So let us see how the program flow control happens when the interrupt is there and interrupt is not there, without interrupt and with interrupt. What is the difference? So we can visualize from this slide. So here with no interrupts, mean the device is not sending any interrupt to the processor, device is there is no communication from device to the processor. In that case, that is the usually happen in a programmed IO. So here whenever the write operation, any IO operation is required, processor will initiate the IO operation by sending the commands and then waiting for the device to be ready. Once the device give the data, then it fetch the data and store the data into the memory and come back to the program. So this is the way how it happens. In case of the interrupt, whenever IO operation is required, processor initiate the IO program, send the initial control and command, and now it is not waiting, it is not busy with this activity, it is come back and do the another program. And once the device is ready, it send the signal, interrupt signal that indicates, okay, I am ready with that data, then it completes the IO operation or that data transfer, it can finish it. So here this is the advantage we are getting, processor don't have to wait here. In the earlier case, processor was waiting for that device. So this is the example of short IO wait. Sometime IO wait can be longer as well. Before the next IO operation, the previous IO operation is not completed. That depends upon the slowness of the device. If the device is very slow, in that case it can happen. So that here it is shown here. So the difference is, in case of the interrupt, processor, some time of the processor is utilized. The only overhead is there, that's the context switching. Because at this moment processor is doing something else and the device interrupt the processor, indicate, okay, I am ready with the data. So processor has to, current program has to save, the context has to be saved and jump to the interrupt handler program, finish this thing and come back again after restoring the values. But here, though no context switching is required, processor is continuously periodically checking the status. Once it is complete, then only it execute next. So no context switching is there. So that is the overhead, you can say, in terms of the in the interrupt driven IO compared to the programmed IO. But this overhead is give the advantage in the terms of that only this overhead part is very small, but the advantage the processor is getting by doing some other work, that is more compared to that overhead. So now the next thing is that how the device will be identified in case of the interrupt is generated now. So in interrupt generation, how the device will be identified, which device has generated the interrupt, because the multiple peripheral devices are connected, multiple modules are there. So which device generate the interrupt or interrupt signal enabled, how the processor know. So for this, one solution is that multiple interrupt lines. For each device, let us say I have one interrupt device is there, interrupt signal is there. So it will be like that. You have the processor and interrupt signals are there. These are all interrupt signals. So these interrupt signals are coming via these IO modules. But how many signals? There are a lot of devices are there. For each device, number of ultimately the signals will not be sufficient. All these lines, signals means these are the lines actually. So first of all, these extra lines are required, and you cannot provide, it is totally impractical to provide one line to each IO devices as number of devices are increasing. So that solution is not good. Second solution is the software polling. Means once the interrupt line is enabled, let us say one interrupt line is there and processor checks after the completion of the current instruction execution, then it will check, okay, interrupt is enabled, then it will go to that check interrupt, and then it will branch to a program that is called as a interrupt service routine program, ISR. This interrupt service routine program have the list of all the devices. So, from this then ISR will poll each IO module, because addresses are there in the ISR program. So, from one by one it will poll the modules to identify which module caused the interrupt. So, one by one it will check. Let us say 20 IO modules are there. So, for the each module it will check one by one. It is a time consuming process. So, what happened once? So, one by one it will check, and at the device which initiated or generated the interrupt, that device will indicate via providing the word means that unique identifier for that device on that address lines. So, through that it will indicate, or some acknowledge, through some acknowledge it will indicate, okay, I have initiated this interrupt signal, and then to complete that IO operation, the corresponding interrupt handler program. So, either it will provide, that can be taken from the ISR program, or it can be this address of that interrupt handler can be provided by that device, that is called as a vector. So, interrupt vector will be put on the address lines, and by using this interrupt vector, the processor will jump to interrupt handler program. By taking this address, PC will be loaded with this value, and it will execute the instructions written there to complete the IO operation. Next is a hardware poll. So, in hardware poll, all the IO modules share a common interrupt request line. Means this is a common interrupt, let us say this is interrupt request line IR, and all the devices are connected, modules I say, IO modules are connected, let us say 3 modules are there, 1, 2, 3. Each module supporting, let us say, multiple IO devices, and this interrupt ACK line is daisy chained through the modules. So, this is ACK line, that is daisy chained to all the modules. So, this is the daisy, meaning of the daisy chain means this is the way how it is done. Now, requesting module places the address of the IO module on data bus, which is called as a vector. So, now how it works? Processor checks the interrupt signal is enabled. Now, it has to identify which device has enabled this interrupt signal, and devices or the modules are daisy chains as I shown in this picture. Now, once the processor sends the acknowledgement, says that, okay, I want to process or service this interrupt. So, it will send the acknowledgement, acknowledge that, okay, interrupt is identified, and now it is trying to identify the device. So, acknowledgement signal will go to the first device, here it should be 1, first device it will go. If this device has generated the interrupt, then this device will put the address of the, or this module, let us say, address of the device, address of this module, it will put on the address lines of the system bus, and through that address lines the processor will find that this device has generated, and then corresponding interrupt handler program will be executed. If this device has not generated the interrupt, then this device will pass this acknowledgement signal to the next device. So, only one device will be, if the multiple devices are there, then anyway, so let us say this device first, because this comes in this daisy chain, this device comes at a first. So, if this device is generated, then it will not pass. So, it is guaranteed that, okay, at a time only one device will be entertained. So, this is the way how it works. Now, these devices can be arranged in a priority order. Higher priority devices can be put in this daisy chain first, and then lower priority then. So, such that the priority wise devices can be treated. and this technique is called as a vectored interrupt. Now the next, in case of the multiple interrupts, so there are ways through that the multiple interrupts can handled, because multiple devices that definitely there is no solution that says okay processor can handle 2 interrupts at a time. Definitely either they will be done in the sequence one after another, or maybe one interrupt can also be interrupted by another higher priority interrupt. This is the example of handling the multiple interrupts in a sequential order. So here user program is there, interrupt is generated by some module, processor either through the software polling or hardware polling, the processor will jump to identify the device by any other mechanism. Hardware polling is fast compared to the software polling, because the hardware solution, hardware signal process fast compared to the program execution, because ISR is nothing but is a program. So one by one instruction reading and checking the device whether which device has generated. The device which has generated the signal, that will respond, and then that will be handled. In case of the hardware, it is through the hardware circuit. So it is hardware circuit is always faster than, so that's why this hardware polling is better than software polling. So whatever mechanism is there, usually daisy chain is used in the most of the systems, but whatever mechanism is there, first it will complete the, let's say first device which respond to the interrupt acknowledgement signal by the processor, it will provide the vector or address. By using this address, that IO operation will be completed by the processor, and then the next it will check again the interrupt signal is enabled, then it will go for the next interrupt processing. So in the sequence it does. So the pending interrupts are checked after the first interrupt has been processed. Now next is, if the devices are prioritized, with some devices we cannot stop these devices. Stop in the sense, if they need, the operation has to be completed right now, we cannot say that okay that device wait for some time, because this waiting can incur the data loss. Say for example, the network interface card that generate an interrupt processor to read the data from the buffer and put into the memory. So in that case, because the communication, it is connected to the internet and through that it is getting the data continuously, if this device is not entertained immediately or in a given specified of time, then the data loss chances are there. That buffer will be overwritten by some new data. So this has to be treated immediately. So we have priority to the disk, priority to the devices. Let's say keyboard, disk and printer, all devices can give some priority number on which, if they simultaneously access the simultaneously generate the interrupt, then which device will be entertained first and which second and all. So in that case, one interrupt which is currently processing, that also can be stopped, like a program is stopped. So interrupt also can be interrupted, and then the higher priority interrupt can be processed first. So you can see here user program is there, and then printer ISR come at a t equals to 10, and at t equals to 40 this, okay, it will take 30 unit of time. In between at t equals to 15 a communication ISR come, interrupt service routine, for the communication, as I said that for the network interface card. So that is higher priority device, because data loss can happen if this is not entertained immediately. So that's why this interrupt, printer interrupt is interrupted, and at t equals to 15 to t equals to 25 time, 10 unit duration, this interrupt has been entertained or serviced. Then at t equals to 25, let's say disk ISR is there, because disk also read the data in the block of data. So next block will come before the buffer, if the buffer will be overwritten by the next block, then the previous block will be lost. that information will be lost. Then again this information or that data has to be again provided, because it found that okay, this one block of data is missed, so that it will be a overhead. So disk also have the higher priority than the printer. So that's why at t equals to 25 disk service or disk interrupt is entertained, and after that finishing these two interrupts, then the printer interrupt is completed, and then program processor returns to the user program. So the low priority interrupts can be interrupted by higher priority interrupts. So finally look at some review questions for this lecture. So few questions I have put here. Let me read one by one. When a device interrupt occurs, how does the processor determine which device issued the interrupt? So some solutions we have discussed. So I think you can answer this question. Second is, what is a context switching in terms of interrupt? Third is, how the programmed I/O is different from interrupt driven I/O. Both are the techniques for handling the I/O. How these two techniques are different? What are the plus and minus of each of these method? Fourth is, how the software polling is different from daisy chain method to handle the multiple interrupts. So these are the 4 questions you can try out. So let's look at the summary of this lecture, today's lecture. So I talked about the I/O modules, how the peripheral devices are used to connect to the processor, not with a direct connection, need a interface circuit called as a module. What are the function of this module? What are the structure of a module? What are the I/O methods are there? Programmed I/O. In the programmed I/O, we talked about 2 types of addressing mechanism: memory mapped I/O and isolated I/O, and interrupt driven I/O. In this, interrupt handling and the processing we have discussed, and for the device identification we talked about the methods of software polling, hardware polling, etc. So thank you very much. Have a nice day.